Antibiotics given at scale to young children in sub-Saharan Africa repeatedly reduces childhood mortality. That's not really a question anymore. What is in question is what repeated population-level antibiotic use does to antimicrobial resistance, and whether that signal looks different depending on which age group you treat. This new Nature Medicine paper sits right at that tension point, and it's also a really good example of why a more complex trial design is sometimes exactly what the question needs. I'm Dr. Susan Heavey, Associate Professor at UCL, and this is Further Reading. In this video, I'm going to walk through this recent open access Nature Medicine paper from the AVENIR program that looks at the effects of mass azithromycin distribution on an antibiotic resistance in young children. Now, mass azithromycin distribution has repeatedly been shown to reduce all-cause childhood mortality in parts of sub-Saharan Africa, including Niger. But alongside these benefits, there's a long-standing and very reasonable concern about whether repeated population-level antibiotic use selects for antimicrobial resistance. This study sits directly at that tension point. It asks a very specific question. How does giving azithromycin every 6 months to different age groups of children affect macrolide resistance in the gut and in the nasopharynx at the community level? Now, the trial itself is a large, double-blind, cluster randomised, placebo-controlled study conducted in rural Niger. Communities were randomised to one of 3 strategies: azithromycin given to all children aged 1 to 59 months, azithromycin given only to infants aged 1 to 11 months, or placebo. What the authors found is that repeated azithromycin distribution to the broader age group was associated with a measurable increase in macrolide resistance genes in the gut, but not in the nasopharynx. Treating infants alone did not produce the same signal, and importantly, there was no evidence of co-selection for resistance to other antibiotic classes. This paper is useful, not just because of the results, although they are certainly useful in and of themselves, but also because how it gets there. It's a good example of why simple 2-arm trials are sometimes insufficient, why cluster randomization is necessary for community-level interventions, and how outcome choice and statistical analysis follow directly from the study design. So, in this video, I'll start with a concise figure-by-figure walkthrough to establish what was done and what was observed, as I generally do on this channel. Then I'll step back and unpack the trial design, link it explicitly to concepts from trial design and statistics lectures that I give, and think critically about what this study does and does not tell us about antimicrobial resistance in real-world public health programs. All right, first, a quick figure-by-figure tour. The aim here is simple. What does each figure contribute to the argument of the paper? I'll describe what was done and what was shown without doing full interpretation yet. So figure 1 is the geographic anchor of the paper. This study is embedded in the AVENIR program in rural Niger. This map shows the Dosso province and surrounding countries, with each point representing a community included in the antimicrobial resistance sub-study, 150 communities in total. The main thing to take away from this figure is that we're dealing with a community-level intervention in real communities across a defined region, and that immediately explains why individual randomization would be awkward here and why the unit of randomization becomes the community. Figure 2 is the design skeleton. The parent trial randomized 3,000 communities into 3 arms. One arm where children aged 1 to 59 months received azithromycin every 6 months. A second arm where infants aged 1 to 11 months received azithromycin and older children who received placebo. And a third arm where children aged 1 to 59 months received placebo. For the antimicrobial resistance analysis in this paper, they selected 150 communities, so 50 per arm, and within each community they sampled roughly 30 children for rectal and nasopharyngeal swabs. Those samples were pooled at the community level and analysed after 4 rounds of treatment at the 24-month time point. Now, a small but important practical note here. Coverage across the 4 rounds is high, roughly in the low to mid 90% range across groups, which matters when you later interpret an intention to treat style real-world effect. So now we're at the who, what, and when. The next figure will then show the core outcomes. Figure 3 is the centre of gravity for this paper. The co-primary outcome here is macrolide antimicrobial resistance measured genetically, and they look at it in two compartments, the gut and the nasopharynx. Let's start with figure 3a, gut macrolide resistance at the class level. So compared with placebo, communities where children aged 1 to 59 months received azithromycin show a statistically significant increase in gut macrolide resistance determinants, about 1.16-fold increase, with confidence intervals that don't cross 1 and a p-value below 0.01. The infant-only strategy doesn't show the same signal versus placebo. The fold change is close to 1 and not statistically significant, and the child-treated arm is also higher than the infant-treated arm. Now look at panel 3C, the nasopharynx. Here, the fold changes are more uncertain and the differences are not statistically significant between arms with wide confidence intervals. Panels 3B and 3D drill down to specific resistance gene, that's ERMF. In the gut, ERMF shows a strong increase in the child-treated communities. That gene appears to be maybe driving much of the gut signal, whereas in the nasopharynx, it's not showing the same pattern. The headline message of figure 3 is clear. Clear gut signal, no nasopharynx signal. And so therefore, the compartment matters. Next, they ask a very sensible follow-up. Is this macrolide effect spilling over into resistance to other antibiotic classes? Figure 4 looks beyond macrolides. They evaluate a broad set of non-macrolide antibiotic resistance classes, including beta-lactams, in both gut and nasopharyngeal samples. The key finding here is negative, and that's important across the comparisons, child versus placebo, infant versus placebo, and child versus infant. They do not see notable differences suggesting co-selection for other antibiotic classes in either compartment. So in the window that they've measured, the resistance signal is specific rather than broad. Finally, they'll go on to look at the microbiome itself, so not just resistance genes. Figure 5 places the resistome findings in a microbiome context. Panel 5A is essentially a who's there overview, so the major genera in the gut and in the nasopharynx across 3 different arms. Panel 5B looks at alpha diversity, so how diverse these communities are. 6 months after the final distribution, there aren't clear differences in diversity metrics across groups in either compartment. Panel 5C is where it gets more specific, so differential abundance analysis identifies particular taxa that shift between arms. And the authors point out that several of the taxa that differ are documented carriers of ERMF, which provides a plausible link between a taxonomic shift and the resistance gene signal we saw earlier in figure 3. So the message here is the overall community structure looks broadly similar at this follow-up point, but there are specific interpretable shifts that help contextualize the resistance findings. So that was the figure story in brief, where the study happened, how it was designed, the key gut versus nasopharynx resistance results, the lack of broad co-selection to other drug classes, and the microbiome context. Now we can step back and do the part that's most useful in terms of connecting this back to your learning around trial design and stats. So why this design was chosen here, what it brought them, and what trade-offs it introduced. Okay, so one of the reasons why I chose this particular paper was that I thought it was going to be an interesting one to talk about in terms of not just the findings, but the actual trial design. So what would a more quote-unquote standard trial design look like? Well, if you were approaching this question in a more conventional way, the simplest design might be a 2-arm individually randomized control trial. You might randomize individual children to receive azithromycin or placebo, follow them over time, and then compare rates of antimicrobial resistance between the 2 groups. That kind of design works well when the intervention acts primarily at the individual level, when contamination between participants is minimal, and when the outcomes that you care about are individual. But even at that stage, you can already see some problems. So azithromycin is being distributed at scale within communities already. Children live together, share environments, share microbes, and resistance genes don't respect individual randomization boundaries. So if you've taken lectures on trial design, you have probably seen that trial design follows the level at which an intervention operates. One of the key distinctions that is introduced between individual level interventions and cluster level interventions. Now, mass drug administration is very clearly a cluster level intervention. The decision to treat is made at the community level, the exposure is shared, and the downstream effects, particularly for something like antimicrobial resistance, are also very much shared. So that really rules out individual randomization as a clean option and instead pushes towards a cluster randomized design where the unit of randomization is the community rather than the individual. Now, how this particular paper differs from a quote-unquote simple cluster RCT, well, even within cluster randomized trials, this study is a little bit more complex. It could still have a standard two-arm design, but rather than simply comparing azithromycin versus placebo at the community level, the authors here introduce 3 arms, so based on age targeting strategies, treating all children aged 1 to 59 months, treating infants aged 0 to 11 months, or treating no children. Now, this is a good example of what you've probably heard referred to as a design that embeds policy-relevant comparisons. The question here isn't just, does azithromycin select for resistance, but does how we target azithromycin matter? That's not really a question a two-arm trial could answer. Now, there are 2 main reasons why this more complex design is justified. First, the policy context. So WHO guidance has recommended targeting infants only as a way of balancing mortality benefit against antimicrobial resistance risk. To evaluate that recommendation properly, you do need an explicit infant-only arm. And secondly, the biology. So resistance selection doesn't just depend on whether antibiotics are useful, but how widely they're used within a microbial ecosystem. Treating a narrow age gap versus a broad one plausibly produces different selection pressures. We know that the adaptive immune system in a baby under a year is quite different to that of a young child. And so really the biology is going to be completely different between these 2 groups, and that is something that needs to be accounted for. So the added complexity here, it's not like gratuitous trial design. It's directly tied to the question the research needs and what they're really trying to answer. So was this the right design? Well, complexity always comes with trade-offs, and it's important not to assume that a more complex design is automatically a better one. One strength of this design is that it allows head-to-head comparison of policy-relevant strategies under real-world conditions at the level where the intervention actually operates. It also reduces certain biases. So, for example, contamination, that would be very difficult to control in an individually randomized trial. But there's also limitations because the unit of analysis is the community. The effective sample size is much smaller than the number of individual children sampled. Pooling samples at the community level also means you do lose individual level resolution, of course. And because this is a large pragmatic trial, some mechanistic questions, for example, exactly how resistance genes move between hosts, are necessarily left unanswered. Taken together, this makes this study a really nice example for teaching, not because it's perfect, but because it illustrates how design choices reflect scientific priorities, ethical restraints, and policy needs. It shows why simpler designs are sometimes inadequate, how added complexity can be justified, and why every design involves compromise. Crucially, it sets us up to understand why the statistical analysis looks the way it does, because once you understand the design, the analysis then follows naturally. With that in mind, the next step is to look more closely at the statistical analysis done here and to connect it back to the types of data being generated and the concepts that have been covered in other videos and most likely in any lectures that you're taking in these topics. Okay, so now that we've done the figure tour and talked about why the design is more complex than a standard two-arm trial, let's do the statistics properly. And by that I mean, let's use the same logic that is used when you learn statistics as an undergrad or postgrad in your lectures. So what type of data are we looking at? How are they summarized? What hypothesis is being tested? What do the p-values and confidence intervals actually mean in context? Now, when we teach statistics, we tend to start with a deceptively simple question: what is data? in research terms, is values that a variable takes for each subject, or in this case, for each community. The next step is types of variables based on data type, quantitative versus categorical. Here, the primary outcomes aren't things like blood pressure or symptom score, they're sequencing-based measures, normalized reads of antimicrobial resistance determinants reported at the antibiotic class level and gene level in pooled rectal and pooled nasopharyngeal samples. That means we're mainly dealing with quantitative variables, but not the classic continuous variables like height or weight. They're closer to counted variables because they originate from read counts, then they're normalized and transformed for analysis. Usually when you're learning stats, you then move on to summary statistics. These are ways of summarizing essential information in a dataset, and they remind us that distribution matters. That's normal versus non-normal distributions. In lectures, we say that the rule of thumb is quantitative variables with a normal distribution are often summarized with mean and standard deviation, and non-normal variables often with median and quartiles. Now, in this paper, the authors explicitly acknowledge that there's a distributional issue and use a transformation before comparing groups. They use log2 transformation of normalized reads to account for sequencing depth and scaling. And then they exponentiate mean differences to get fold changes. This is not unusual, so if the raw scale is awkward or skewed, you do often transform so that the comparisons behave better, then you interpret the results on a meaningful scale. Here, that's fold change. Now, as you learn more about statistics, you start to get more precise about language. We don't just wave our arms around saying, hey, there's a difference. We're testing a specific hypothesis, usually phrased as a null hypothesis. There is no difference between groups, against an alternative hypothesis. There is a difference between groups. So what are the groups here? Well, there's 3 trial arms, communities assigned to azithromycin for children aged 1 to 59 months, azithromycin for infants aged 1 to 11 months with placebo for older children, and placebo for 1 to 59 months. And what's the outcome? The load of macrolide resistance determinants, separately for gut and nasopharynx, measured at the community level. Now, when the paper reports p-values, those p-values are answering a question that you've been taught probably in any stats lectures that you've taken. How compatible are the observed group differences with the test hypothesis under the chosen model and assumptions? If you're learning stats, then you will have also been introduced to the concept of alpha error. That's the false positive risk. And it'll be explained why repeated testing increases your chances of finding something significant just by chance. That becomes very real in a 3-arm trial with multiple outcomes and multiple compartments. This paper addresses that by using a hierarchical gatekeeping procedure for the primary macrolide resistance comparisons in a pre-specified order. Child versus placebo first, then infant versus placebo, then infant versus child. In plain terms, they don't treat every comparison as equally free. They control the family-wise error rate by only moving down the list if earlier comparisons clear the threshold. For broader secondary comparisons across many non-macrolide classes, they use a false discovery rate approach, which is another standard way of handling multiple comparisons when the question is broader and more exploratory. Another thing that we talk about in our lectures, and that I'm sure is covered in any stats modules that you're taking, is that statistical significance is not the whole story. And another conceptual tool that you should be comfortable with is confidence intervals. So this paper reports fold changes with 95% confidence intervals. For example, in the gut, the fold change in macrolide resistance determinants for child azithromycin versus placebo is 1.16, with a confidence interval of 1.06 to 1.28. That interval doesn't cross 1. In the nasopharynx, the fold changes have much wider confidence intervals and the comparisons are not statistically significant. That's a familiar reminder that a non-significant p-value is not necessarily the same thing as no effect. It can also reflect uncertainty and imprecision. In lectures, we also go through a practical principle. So the statistical test depends on the type and distribution of data, the number of groups compared, and whether samples are independent. Here, the authors use pairwise Wilcoxon rank sum tests for the primary comparisons, which is consistent with an approach that makes fewer assumptions about the underlying distribution, especially reasonable when your unit of analysis is a pooled community sample and the data are transformed sequencing measures. Now, one more key stats concept that I'm sure you've heard and been trying to unpack is beta error and power. So that's the risk of missing real differences when the sample size is limited. Now, a subtle but crucial point in this paper is that the N for the resistance analysis is not the huge number of children swabbed, it's the small number of communities. So 50 communities per arm in the sub-study. The authors explicitly include a sample size justification at the community level, for example, estimating power to detect roughly a twofold difference in nasopharyngeal resistance determinants with 50 communities per group. So when you see wide intervals or non-significance in the nasopharynx, it's worth remembering that kind of message that power depends on the effective sample size. And here that's the number of clusters, not the number of patients. Fortunately, with the scale of this study, the number of clusters, though small, is not that small. We're still talking 50 communities per arm. It's not nothing. Now, beyond resistance genes, the paper also uses microbiome community analysis, things like Permanova, for overall community structure and diversity indices like Shannon and inverse Simpson, and differential abundance approaches with false discovery rate thresholds. Now, for the purposes of most basic stats modules, the key takeaway would not be the mechanics of each method, but that the analysis is aligned to the question, do the communities differ overall? Are there any specific taxa enriched, especially taxa known to carry genes like ERMF. So the statistical story here follows the logic of most baseline stats modules pretty perfectly. So you want to identify the type of data, think about the distribution of that data, then choose appropriate summary measures and transformations, specify the test hypothesis, interpret p-values alongside confidence intervals, and control error rates when there are multiple comparisons. Most importantly, once you understand the design and the unit of analysis, the statistical choice makes sense, and you can read the results without overclaiming what they do or don't mean. Okay, thanks for sticking with me this far. Now, before we finish, it's worth being clear about what the study does not tell us, because this can be just as important for reading trials well as understanding what they do show. First, although this paper demonstrates a measurable increase in macrolide resistance genes in the gut at the community level, it does not tell us how these resistance genes translate into clinical outcomes. We don't know from this study alone whether these genetic signals lead to treatment failures, more severe infections, or any long-term health consequences for individual children. Second, because the unit of analysis is the community and the samples are pooled at the community level, we lose individual level resolution. That means that we can't track how resistance emerges within a particular child over time, how long it persists, or how resistance genes move between individuals. Because that's a thing that they do. Side note, yes, we can cover that in another video. Third, the follow-up window here is relatively short in biological terms. The samples are taken 6 months after the final distribution, so this study can't answer any longer-term questions about whether the resistance accumulates, stabilizes, or declines over years or decades. And finally, while this is a very strong real-world study, its findings are necessarily context-specific, shaped by the setting, background antibiotic exposure, and concurrent public health programs. So the results shouldn't be read as universal truths, nor should really any clinical trial results, but as evidence that needs to be interpreted alongside local epidemiology and policy priorities. Always read these kind of papers in context. Now, none of these things are flaws, they're consequences of deliberate design choices, but being explicit about them helps us to read the paper with the right level of confidence and the right level of restraint. Okay, it's time to finish up, and as I do think it's worth to zoom out back to like a bigger picture. So this study, as I said, is situated in a really specific context. So mass azithromycin distribution delivered at scale to whole communities in a setting where childhood mortality remains high and where antibiotics are being used as a population level public health intervention. Now, this looks quite different from how antibiotics are used in places like in the UK or in a lot of the rest of the Western world, where exposure tends to be individual, episodic, and treatment-based, rather than repeated and community-wide. As a result, the resistance patterns that we worry about in most of those settings often involve different organisms, different antibiotic classes, and different selective pressures. Elsewhere globally, the picture is again different, shaped by access to antibiotics, regulation, background use in humans and animals, and the local burden of infectious disease. So the findings here, as I said, should not be read as universally transferable, and that's something that you really should remember across all clinical trial reading, but rather is evidence that helps us to understand how resistance emerges under this particular set of conditions. What this paper does very well is show how study design, statistical analysis, and interpretation have to be aligned, not just to a specific question, but to the context in which that question sits. And that, more than any single result, is what makes this such a useful paper to read, teach from, and think with. If you're teaching stats or trial design, feel free to embed this video under the further reading section of your online learning platform, whether that's Moodle or one of the other ones. Feel free to use it, share it how you like. Hopefully this is useful in teaching. If you're learning trial design and stats, let me know. Did this align well with your kind of stats 101 or clinical trial design 101 type modules? Was it useful for more advanced modules? I'm curious, and I do genuinely take this feedback on board to improve my future videos. So thank you so much. That's it for now, and I will see you next time on Further Reading.